Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to calculate a centroid for a function. So what we're going to do is we're going to look at the function y equals x squared. That's my favorite function to use as examples. I like, it's just I call it the happy function because I like to think of it as an infinite smile. It's also just a kind of nice, easy function to use for examples. And what we're going to do here is we're going to consider the region from 0 to 2. And if we look at the point out here, this would be the point 2, 4. And what we're going to do is we're going to try to calculate the centroid of this bound region here. Now, first thing we do is just like we would do an area calculation, we start by drawing a rectangle. And I'm going to draw my differential rectangle bound within the area that I'm interested in. Okay. I'm sure we're going to need the length of that rectangle. I'm going to go ahead and write that right now. Now, from here to here is the function value, and from here to here is 4. So the length of my rectangle is 4 minus the function, 4 minus x squared. The width of the rectangle, right, that's this dimension. I'm going to call that dx. Now again, whether you call this a dx or a delta x, it depends on how you intend on working the problem. If you're intending on working this numerically in Excel, you can go ahead and call that a delta x. Or if you're intending on using a calculator and breaking it into, say, 6 chunks or something like that, it's perfectly fine to write that as a delta x. However, if you're if you're intending on using an integral process, so the integral process inherently means an infinite number of chunks and a differential width, because if you use an infinite number of chunks, the width becomes infinitely small. Right? Now, the area of that rectangle, right, that'd be this stuff right here, is a differential area. I'm going to go ahead and write that down. It's going to equal the length of the rectangle, 4 minus x squared, times its width, dx. So this product gives me kind of a generic formula for the area of any rectangle anywhere in this region. Now, because I'm after centroids, we're also going to want the centroid of the rectangle. Now, rectangle is a nice uniform geometry, so its centroid is in its geometric center. The x-coordinate of its centroid is just that, x, that distance. The y-coordinate of the centroid, interesting. In this picture, that's this distance. You notice it's not equal to the function value. It's also not equal to 4. And it's also not equal to the difference between them. If I take 4 minus f of x, what I get is the length of the rectangle. You'll notice that that dot is halfway between the 4 and the function value. So it's equal to the average of the two. I'm going to go ahead and write just 4 plus x squared over 2 would give me the y-coordinate of the centroid of that rectangle, because it's halfway between the function value, which is that distance, and 4, which is that distance. All right, so now to get x bar, x-coordinate of the centroid, what we're going to do is we're going to take the x-coordinate of the centroid and we're going to multiply by area, because again, you find these centroids by a weighted average. In this case, we are averaging it by area. So that's the x-coordinate of the centroid times the area. These then need to be added up. That's what the integral does. That's actually an S, stands for sum, like infinite sum. In this case, 0 to 2. Then we need to divide out the total area. So we got to divide this area out. So we're going to be dividing by the integral. Let's see, the length is just 4 minus x squared, and then times dx, and again 0 to 2. So this expression will give us x bar, the x-coordinate of the centroid for this bound region. And let's go ahead and work it out, see what we get. All right, so This product is 4x. By the time we integrate it, that's going to integrate to 4x squared over 2. So I'll call that 2x squared. This product is minus x cubed. That's going to integrate to x to the 4th over 4. And again, that's evaluated 0 to 2. I'm just going to go over that one more time, make sure I did that right. 4x is going to integrate to 4x squared over 2. That's a 2x, yep. And then minus x cubed is going to integrate to minus x to the 4th over 4. All right, in the bottom, integral 4 dx is 4x. And then the integral of minus x squared is minus x to the 3rd over 3. And these are, again, evaluated 0 to 2. So, equals. Would somebody please run this? Let's see, what do we got here? 2, 4, 8 minus, what'd you get? For the top? Or for the whole thing? Would you go ahead and give me just the top and then just the bottom? You got what? Four up top. 8 minus, yeah, that looks right. And then what do we get on the bottom? Pardon me. 8 minus 8 thirds. What's 8 minus 8 thirds? Just give me a decimal. What's that come out to be? Okay. So the area is 5.3, and the reason I had you calculate is we're going to need it for the y-bar calculation. So then we don't have to work out the integral again. Okay, so 4 over 5.3 is about 0.79-ish. Is that right? Yeah. Ish is a technical term for two significant figures. So the x-coordinate of the centroid of our bound area, I'll write this over here, we found is approximately 0.79. I'm going to take a moment here, and actually I'm going to save the picture of that. Okay, now we're going to talk about calculating y-bar. Get rid of this stuff. All right, so what we're going to do here is we are going to take the y-coordinate of the centroid of the rectangle, which is going to be 4 plus x squared over 2. And again, that's y-bar for the rectangle, which came from the average of these two distances, this one and this one. Then we're going to multiply by the area of the rectangle, 4 minus x squared dx. These need to be summed up from 0 to 2. And then we divide by the total area, which we know to be 5.3. All right, so this is going to equal, how about we bring that 1/2 out front, and let me write out one more line. Integral, let's see, when we multiply this out, this is going to be 16, the minus 4x squared plus 4x squared are going to add to 0. Then we're going to have minus x to the 4th dx. Again, that's over 5.3, and the integral is running 0 to 2. Which is going to be, all right, first integral is 16x, minus second integral is x to the 5th over 5, again 0 to 2, and then over 5.3. And I'm just going to take a moment here while I wait for somebody to crunch a number here. I think I'll just kind of freeze this while we wait. We're back here, and popular opinion on this seems to be about 2.4. So our y-bar here for that centroid is approximately 2.4. Again, that's approximately 2.4-ish, being a technical term there for 2 sig figs. So important points of this, how to find a centroid. It's all about the rectangle. You start by drawing your differential element. You will almost always need its length. So you got to write out an expression for the length. Now that expression is going to depend on whether it's horizontal or vertical. It's going to depend on, is it above this function or not. That's going to vary a little bit case by case. You will need the area of that rectangle, which is length times width. Then to get x bar, you just integrate x times the area from 0 to 2, divide out the total area. To get y bar, you integrate the y coordinate of the centroid of the rectangle times the area, divide out the total area. And again, the one that tends to throw people for a loop a little bit is the y coordinate of the centroid. That's this distance in red here. And again, notice that that distance is bigger than this distance, the function value, but smaller than the 4. In fact, it's halfway in between them because the rectangle has a uniform geometry. That's why y bar is the average in this example of 4 and x squared. That's why it's 4 plus x squared over 2. So this is y bar for this vertical rectangle. And again, and then times the area of the rectangle, add it up, divide by the total area. And that's how you find the center of area, or the centroid of this geometry. Hope this video helps demonstrate these things. Have a great day.